Okay, so we're ready to talk about the second law of thermodynamics. And so this is our second module in the lecture series. I'll break it up into a lot of smaller units. But first, what I want to do before I talk about entropy and spontaneity, I want to talk a little bit about just the first law of thermodynamics again. So when we take an object, and let's say this is my surroundings, and this is my system, okay? Now, this could be an object like a piece of metal, it could be a chemical reaction, but it's anything within the surroundings, and there's a heat transfer going on. So there's energy transfer. And it could be going in either direction, but what we always say is that the Q of the sys plus the Q of the surroundings is equal to 0. And this is conservation of energy. That's first law. And, it feels right in a sense. Like, oh yeah, I can't lose anything because I always have to make an even exchange. The system's energy is always the opposite of the surroundings energy, and that seems kind of like that's the way it should be. So here's the second law. Second law of thermodynamics says the entropy of the universe, so that's a very grand statement, but that's basically everything, right? Is equal to the system plus the surroundings. Okay, so we're going to say something like this. Delta S of the system plus delta S of the surroundings. This is my delta S of the universe, okay? So this really should say entropy change of the universe increases for any spontaneous system. So what does that mean? Well, if this was the first law of thermodynamics, we would just say this, and that would be conservation. But we're looking at the second law of thermodynamics, and it says it's this. And there's very good reasons to say it, but we can't really talk about it yet until we've covered some background material. Okay, so this is for anything that's spontaneous. You could also go forward and say delta S of the sys plus delta S of the surroundings. I see what I did there now. Gosh. Like that, right, is less than 0 for a non-spontaneous reaction. And that kind of makes us feel better, actually, because you say, well, you get more entropy this way, and then you get less entropy this way, so it all, in total, should just balance out, right? And the answer is actually no, because the only processes that take place are the ones that are spontaneous. And the non-spontaneous processes are not actually taking place in the direction we're wanting, right? They're always favoring the reactant side instead of the product side. So in other words, just looking at these two statements, the entropy of the universe is constantly increasing because only the spontaneous processes take place. Okay, so then the question is, what is entropy? So I think I'll just state this right off the top. There's some confusion about what entropy is because we try to think of entropy as like a single thing, okay? And in fact, scientists have two different ways they like to talk about entropy. One is like a picture, right? And disorder and possible states of a system. So let's say I had a well-organized set of pins that look like this. That's my ordered state. And then we would look at the after picture, right? And maybe the pins, some are still standing up, some are poking out in different directions, right? I'm not counting. Let's just say that's about the same number. When you go from this to this, we think about this as more possible states. And in practice, it looks disorganized. Here, this is ordered with few possible states. This is disordered with more possible states. This would be an increase in entropy is positive for that process. And so we'd like to think of it in terms of pictures of how things look before and after. And that's actually a valid way to look at entropy. But the other way to look at it is something called energy dispersal. And that's more like the movie picture version. So how did you go between this process to this process in order to become more disorganized? Okay, so how would something like this happen, right? This is a spontaneous process that takes place for these pins to go from the organized state to the disorganized state. And part of that has to do with energy transferal. So if I'm putting energy in this system, if this is the one state that they have when they're organized, by putting energy in the system, I can create more possible states. And so we think about this energy dispersal as delta S is equal to Q divided by T. T is the temperature in Kelvin. And then Q is the heat. So when we talk about energy flowing from one part, let's say from the system to the surroundings, or from the surroundings to the system, part of what that energy does is create disorder, because with the extra energy, the molecules that are receiving the energy, right, can have more possible states available to them. So if you think of this as a crystal of ice, and then you think of this as water molecules, that's what the heat energy can be doing, is creating more states for the molecules to be in. So if an object is hot, it can transfer energy to an object that is cold, right? But why is that? I mean, why does heat go from hot to cold? Does anything have to happen for that process, right? And we know that that process, just by default, it's kind of the natural thing, right? It happens spontaneously. And it turns out this is driven by the processes or the principles of energy dispersion. And so we're going to look at that in the next slide. Like, why does the second law of what does the second law of thermodynamics say about that process? Okay, so here's my system, right? And my surrounding, and the system's hot. So this is going to be T sys. And then the surroundings is cooler, that's why I drew it blue. And so we know heat transfer goes from this direction to this direction. So there's T surroundings. And we know just by default then, just from our observation, right, T of the surroundings is less than T of the system. Now, energy dispersal, the concept of energy dispersal is that delta S is equal to Q over T. And we know that the entropy of the universe is delta S of the system, right, plus delta S of the surroundings. So in other words, this is equal delta S of the U. I'm just going to put a U down there like that. Okay, so conservation of energy, now this is important, right, is still taking place. I have a Q for the system, and I have a Q for the surroundings. And I know that Q of the system plus Q of the surroundings, I don't know why I drew S, Q of the system plus Q of the surroundings, I know that's equal to 0. That's conservation of energy. Now, if I say Q sys equals, then it's equal to minus Q of the surroundings. In other words, they're opposite in sign to each other. So what I'm going to do is this, as I'm going to take and I'm going to substitute this in for each of these and then give the appropriate subscripts for it. So I know delta S of the universe is equal to, and then it's going to be Q Now that's the system, right? So that's Q of the system divided by T of the system plus Q of the surroundings divided by T of the surroundings. Okay, so what do I know, right? One of the things I know from conservation of energy is that if this is negative, this is positive, and vice versa. If this is negative, this one's positive. The other thing that I know is that energy is flowing from the system to the surroundings because the temperature of the system is actually greater than the temperature of the surroundings, is what I said over here. So that being the case, right, the sign of Q cis is actually negative. And the sign of Q surroundings is positive because this process is transferring energy from one to the other. The other thing that I just said, though, is Q of the system, right, is actually larger than Q of the surroundings. Otherwise, it doesn't flow. Heat doesn't flow. What's the result of that? For any spontaneous flow of heat, energy, right? What has to be true is that the entropy of the surroundings has got to be bigger than the entropy of the system. And that means the entropy of the universe is positive. So the second law of thermodynamics is essentially proved by this kind of reasoning. And I got to be careful when I say proved. It's shown to be generally true because of this kind of reasoning. I mean, if there was a situation that ever showed itself where heat flowed in the opposite direction from the energy levels of the system and the surroundings, so it might not just be temperature, but it could be other things, then we would have a violation of the second law of thermodynamics. And in all the years that people have been doing stuff like this, it's actually never been shown to be true. You're always losing out, basically, because you're always becoming more disordered. There's this cute little saying in second law of thermodynamic language about not being able to break even, and you can read about that because I can't even remember what the saying is. But I can remember this, but I can't remember what the little saying is. But basically, entropy is always going to increase. Right? And then, in a sense, you're always losing energy to the increase in entropy. You can never get some of this energy back because in order to get it back, you have to think, well, then I'll just undo what I just did. But then you have to make a non-spontaneous process spontaneous. And just in the fact of doing that, trying to reorganize things, you lose energy. So you could think of it like this, right? You have a room, I'm assuming, where you're living. And for most people, especially college-aged people, their rooms are messy. And I will admit my room is messy. It becomes messy spontaneously. But in order to get it clean, I've got to expend a ton of energy just to get it back clean. And once I do that, I just know over time, spontaneously, it's going to degrade over time. And that's sort of this analogy here, right? There's a constant loss of usable energy because of this constant disordering of the universe. So the next little segment we're going to talk about is the other view, like the picture view of entropy, right? And we're going to look at energy and in terms of available states. Now, when you have more energy, you have more states available. And there's a lot of ways that you can do this. But if you really want to make a strong argument for entropy and availability of states, you could really go all the way down to the atomic level. And if you remember, like ground state orbital diagrams. So let's do nitrogen. Not that you remember off the top of your head, but nitrogen would look like this. This is 2s. So that's the ground state. How many ways are there to organize this? Well, really, if all the electrons are spinning in the same direction, right, then there's just one way to do that. On the other hand, if I put a slight amount of energy into my system, I could take, so this is ground state nitrogen, this is 2p, And I'm going to look at a very small excited state. And this small excited state is simply to violate what we called Hund's rules. Hund's rules give us the lowest energy configuration. And what Hund said is that in order to have the ground state, all the electrons need to be in separate orbitals before pairing with their spins parallel. Okay, so the small perturbation then I'll put in here is I'll put just enough energy in here to turn this electron over. Now that's not much energy, right? But how many states are there now? Right? How many possible ways are there to have one electron upside down? And the answer is there's 3. So in other words, I could have a state where the p orbitals look like this. Or I could have a set of p orbitals where the states look like this. So just that small amount of energy increased the number of available states. And we do see, for example, changes in entropy in molecules just by adding a small amount of energy to them so they can, for example, vibrate in a slightly different fashion. Okay, they can either wiggle or they can stretch, but they can only do one at low energy. And as you add a little bit of energy, the amount of wiggling that happens changes. Okay, so at a very, very, very basic level, energy affects the number of states that are available. Okay, so here's another interesting example of looking at states and understanding how entropy changes. Let's say you just have 2 cylinders or 2 like spheres connected by a valve, and you have gas in one side and this side's a vacuum. So let me ask the question, if you don't allow any heat to exchange, that is, you completely isolate this, right, and you open the valve, what happens? And most people will answer this by saying, well, the gas will move until both sides have the same pressure, and then they'll stop moving. The gas will stop moving. Well, in reality, there's an equilibrium there, and we'll get into the equilibrium part later. There's some gas molecules going left and right, and some going right and left. But let's just pretend that it's static, okay? And that's really what this view is. It's sort of the static view. So nobody thinks, usually, occasionally there are people that think this, but nobody usually thinks, well, when I open up the valve, all the gas is going to go on the other side and there'll be vacuum on the left, right? Nobody thinks like they're going to just, all this gas is going to go here and be a vacuum. And nobody also thinks like if you open the valve, like all the gas will stay in here. Because you know there's gas molecules in here, there's no gas molecules in here. It's going to move. Delta S for, this is my universe now, my whole system and surrounding. My delta S is the delta S of this and the delta S of this, right? Or I should say the S of the left side and the S of the right side. I have an entropy, and what I'm going to look at is I'm going to look at what happens when I open the valve. And in order to do that, I'm going to use one of my favorite analogies for this. It's super simple. It's the world's tiniest cylinders with a valve in between it. Okay, and it looks like this. So now my cylinders are so small that I can only put in 3 gas molecules on one side. But right now I only have 2. And there are what we call microstates or microscopic states, okay, in which if I have the valve closed, that's what that's supposed to represent, the gas being all to the left or all to the right can be described by 3 different states, where these are sort of like the electrons, right? They can only have one, or they have the one orientation. And so what ends up happening is I got a state with at the top, I have them with at the bottom, and I have one at the top and one at the bottom. So there's 3 states here, and then all in the other side, right? There's only 3 states as well by analogy. That represents all the molecules going over to this state and just leaving this state altogether. Then the question is, how many states are there when I open the valve up, right? And the answer looks like this. With one sphere on each side, there's 1, 2, 3. Then I just move this down 1, 4, 5, 6, right, 7, 8, 9 different microstates. In other words, there's a lot more ways, even without energy transferal, there's a lot more ways for the two gas molecules to be organized when the valve is open. Okay, so this goes back kind of to that analogy that I gave you before, that you're walking down and you have pathways in front of you that are all in equal energy states, right? That is, you're here and you hit a crossroads here, and you could go right or left, and both ways are equally attractive to you. Then the chances of you going to the left or to the right, this is you as a dot on Google Maps, is the same. So you'd be either going to the right or the left. Now, if it was me, I'd be going to the right because I trust going to the right more than I go to the left, and there's no good rationale for that, and that's why I end up lost all the time. But it's always an adventure. Anyways, yeah, that would be me. But if you're a completely rational molecule, you just go one way or the other. Okay, so, but if you have more choices in one direction, then what happens is you're going to choose this twice as often as you choose that. Because, right, if all are equally the same, you're going to choose this 4 times out of 6, and this only 2 times out of 6. So this is what this is. It's a zero energy difference. There's no energy being allowed into our system, right? And as a result, you could either be all on the left side or the right side, but when you open it up, there are way more opportunities for everything to be in the middle. Now, in the composite with just these two gas molecules, right? This is part of the big picture. So 6 times versus 9 times, right? 6 times are either the left or the right. 3 times is to the left, 3 times is to the right, but 9 times it's in the middle. That is 1 on each side. Turns out if you go through this analysis and you try to do 4, right? 4 here, what you find is there's a very diminishing percentage of the time that you're going to be either on the left or the right. So just a small increase. Now you think about, this is 2 molecules, and normally we're making this decision with an Avogadro's number worth of molecules, right? It's basically going to tell you, yeah, it's going to be even on both sides because there's way more states with even amounts of molecules on each side rather than all on one side or all on the other. Okay, so here's a kind of a interesting example of an application of entropy to a physical process, and that's to freezing. Like, you're going to freeze water and make ice, right? Okay, so the making of ice is an exothermic process. Okay, so and actually delta H, so H2O liquid going to H2O solid. Delta H is around 6 kilojoules per mole, negative. And it's negative because in order to get it to be in the solid state, right, you have to remove some energy out of it. So what's happening is, as you're trying to freeze this liquid in a test tube, heat is being transferred from the system to its surroundings. So Q has a negative sign. Out here, Q has a positive sign. Now, if you think about that then, right, in order for heat to move, then the T for the system is greater than, I have a weird refrigerator, T of the surroundings. So what does that mean? Well, even though this process is negative, right, and T of the system, but T of the system is larger than T of the surroundings. Now Q negative and Q positive, that's the same amount of energy, right? So if I'm looking at delta S of the universe, that's delta S of the system plus delta S of the surroundings. And what we just said was delta S is going to be negative, but it's actually smaller than the delta S of the surroundings. And so delta S of the universe is positive. So even though you have this process that's exothermic, right, you can, and that should normally be non-spontaneous. Remember, uh, ice doesn't freeze like it, well, I guess it could, but it doesn't really usually freeze at room temperature. The only way you can make this process spontaneous is by dropping the outside temperature, and in the process of doing that, you increase the entropy of the universe. Okay, and you could actually calculate like the actual amount of entropy change per mole for the ice simply because we know the temperature at which ice freezes, right? It's 0 degrees Celsius. I was trying 273.15 Kelvin. I got stuck of saying one and then the other. And this is the energy in kilojoules per mole. So all you have to do to calculate delta S for the ice is say 6 kilojoules per mole and then it's 273.15 Kelvin. Okay, and then sometimes it's asked for in joules, sometimes it asks for in kilojoules, but that's how you would actually calculate that based on the heat for the fusion of ice is what that's called. Oh yeah, one other thing. This is the exact same conclusion we came to all the way back here about how energy transfer takes place, right? Energy transfer takes place because, right, it's hotter on the inside, colder on the inside, and that corresponds to increased entropy in the universe. So this chemical physical process follows exactly the same rules. So I'm not entirely done with entropy here, but I do want to introduce a new concept. It's called the free energy. And we're going to start with entropy of the universe. So we've already sort of looked at this now. We sort of have a good agreement, I hope, of what delta S of the universe is for a spontaneous process. And that is delta S of the universe, right, has to be greater than 0. It's also, though, that delta S of the universe is equal to delta S of the system plus delta S of the surroundings. So these terms have to be greater than 0 for a spontaneous process. Now what we want to do actually is make an equation that's usable and related to variables that we can measure. And stuff about the surroundings is hard. Like, it's hard to know how much heat energy the rest of the universe absorbs and things like that. And so what we're going to do is create an equation based entirely on the system. Now, what is the system that we're most interested in chemistry? And the system is a chemical reaction. So what I'm going to do is I'm just going to cross that out and put Rxn. That is my system. And now the surrounding is everything around the reaction. So what I can write then is I can do one quick substitution. I know that delta S of the surroundings is equal to the Q of the surroundings divided by T. And we talked about that earlier, right? That's the heat dissipation of the version of entropy. And I'm going to substitute that in for delta S of the surroundings. And so now I have delta S for the reaction plus delta S, plus Q of the surroundings over T. Now, here's the catch. what is Q of the surroundings? Well, Q of the surroundings, and I'm going to say negative Q of the surroundings because it just comes out better. The negative of Q of the surroundings is equal to Q of the reaction. And in chemistry, right, that's delta H of the reaction. That's something that we can measure or calculate, for example, using calorimetry of some sort. So this still has to be greater than 0. And what I'm going to do is this. I'm going to say delta S of the reaction. And then I guess I should have left it like this. I apologize. I guess it is better this way. Sometimes as I'm going along, I think, oh, that'll be better. And then I get to it. I'm like, nope, it wasn't. So that's going to be minus delta H of the reaction divided by T. That has to be greater than 0. I'm going to do a little quick math. I'm going to distribute the T, so I don't have like delta H over T. And so I'm going to get T delta S of the reaction minus delta H is greater than 0. And that's delta H of the reaction, so I'll put that down there. And one of the things that we end up doing in this derivation, honestly, it could have gone either way. But what we do is we usually take and multiply both sides by -1. And when you do that, you're going to get delta H minus T delta S is less than 0 for a spontaneous reaction. And this term, this is delta G of the reaction. It's the free energy. So as it turns out, for any spontaneous process, delta G of the reaction will be negative. So spontaneous, there's going to be 3 cases. Delta G is less than 0 or negative, right? For non-spontaneous, delta G will be greater than 0. And then, so in other words, it's positive. And then if the system is such that delta G is equal to 0, the system's at equilibrium. Now, it turns out that'll be concentration dependent, and we'll have to look at that a little bit later. But these are the key things to remember. Spontaneous if it's less than 0, non-spontaneous if it's greater than 0, and then equal to 0, then it's at equilibrium. Okay, so I'm about to get into something we call standard states, or we talk about the standard states in thermodynamics. But before we hit that, we're going to talk about something called the third law of thermodynamics because it's directly related to that concept. So in the third law of thermodynamics, there was a guy, when we were talking about entropy before, all the way back here. Oh, did I pass it? Yeah, I passed it. It's a guy named Ludwig Boltzmann, and Boltzmann said that the entropy as a system is equal to K, which is known as Boltzmann's constant, times the natural log of W. And the W is these microstates that we were talking about. So the natural log of W for this one would be just the natural log of 3, and K is Boltzmann's constant. Now the value is not super important, but it's 1.38 times 10 to the minus 23rd joules per Kelvin. And joules per Kelvin are actually entropy units. So when you take the log of W and you multiply it times this value, that's where the units come from. Okay, so back to Boltzmann's equation, right? It's actually, he's famous for this equation because it is a fundamental equation, but it also is because it's on his tombstone. When he died, he had it engraved, or people engraved it on his tombstone. And he's a very serious looking guy in that tombstone, by the way. But he said and this is the third law of thermodynamics. The entropy of a perfectly ordered crystal at absolute zero, right, is zero. In other words, if you have a perfectly ordered crystal and you have no energy in the system, because remember the energy, if even if you can flip an electron, right, even if you can do that, that causes an increase in the entropy, increases the number of W values, like microstates. So if you have a perfectly ordered crystal, then this value becomes 1, because there's only one state for a perfectly ordered crystal at absolute zero, and then that becomes K times 0. In other words, the entropy is 0. And joules per Kelvin, sorry. Why is that important, right? It turns out when we're talking about like delta H, and in particular, right, one of the attributes of delta H is we don't know that what the zero value of energy is. So we don't have a 0 point, and that's why you always see it listed as a delta H. You never just see H by itself in an equation where you're doing a calculation. Like in theory, we can write things like H is equal to E plus PV. That's like, anyways, from Hess's law stuff, and from thermodynamics from the first semester. But yeah, we don't ever see just H if we're doing a calculation. And the reason is we don't know where 0 is on the scale. So, it's not like a bank account where you know that it's positive or it's negative because you have $0. Like, you know what $0 is. I mean, like, you hope that people know what $0 is. Credit cards just kind of screwed that all up. But yeah, we kind of know where 0 is for money. But for delta H, we don't know where like the 0 is for the enthalpy. And so it is kind of a deal, right, that we actually have this. And so we actually can measure the absolute entropies of substances by a number of different ways, in particular changing temperature and looking at heat flow. Like how much energy does it take to change the temperature of an object from one temperature to another. That graph tells us what the entropy is for that material. Okay, so we're going to talk a little bit now about standard and non-standard states and the equations for them. So what does it mean to be at standard state? Well, standard state is the following: 1 atmosphere for gases, 1 molar for solutions. And oftentimes people get caught up at, oh, well, isn't 25 degrees Celsius or isn't 0 degrees Celsius standard? And it turns out in thermodynamics, those are not part of the standard. The only thing that matters in thermodynamics are these values. Okay, so delta G of a reaction at standard state, this is how we indicate standard state. Literally means that's the value if all the concentrations were at 1 atmosphere or 1 molar concentrations. Now, how do we get these values, right? The way we get these values is we go into the back of the book, and for the delta G of the reaction, this is what we showed in the first set of slides. That's going to be the delta G of the products minus the delta G of the reactants. But these are the free energies of formation, or the free energies of the products based on the delta G's standard of formation. So formation, we talked about that earlier, so I won't go over that again, but it's at 1 atmosphere and 1 molar concentrations. Or pure solids, for example, also would qualify as a part of the standard state. So when you look at that table in the back, that's really for things that are 1 atmosphere, 1 molar. Okay. But if you look at the table for the S values, and I'll show you that here in just a second, all you see at the top of the heading is S. And the reason you see that is those entropy values you see in the table are actually the measured entropy values for those substances. It's the absolute value of it. Now you can still calculate delta S of a reaction, right? But that's going to be S of the products minus S of the reactants. And it's not the delta, it's just it's the absolute entropy of products and reactants. You got to multiply by moles and all that stuff, but it's done slightly differently. So here's that table. I just opened it up from, the Canvas page. And you'll notice here S of, it's not the S of formation, it's just S, right? And that standard state. So this would be for, this is ethine or acetylene gas, right? That means this is the S value measured for acetylene at 1 atmosphere. Okay, that's what that means. Couple others, right? 152.2, that would be for bromine as a liquid, right? Again, that's the pure liquid, pure solids are also part of the standard state. I don't think I said liquids before. And then I wanted to show you a couple of others. I can find them in here. Yeah, look at these ones here, right? So copper ion is listed as minus 26. Now, how could something have negative disorder, right? And this actually falls back to zeroth law of thermodynamics. We can do it for pure substances. We can even do it for pure compounds. But for an ion, right, it's dissolved in solution, and you can't have gotten it without some other ion present. So what they actually did is these are really like standard entropies of formation, and what they did is they assumed that hydrogen ion would be 0. Let's see if we can do my alphabet here. E, F, G, H. A hydrogen ion is given a value of 0 because ions in solution always have to come with something else. And so you can't actually measure their absolute entropy. And so also you can't measure their enthalpies or their free energies as like absolute values. So something has to be given a 0 value. And for all the ions in solution, we go back to hydrogen ion or hydronium ion in water, and that's how we get entropies for all these different ions. So that's why occasionally you'll see negatives here. That just means it has less entropy than hydrogen ion here. Okay?